In this video, I'll talk about how to obtain models for the activity coefficient, and we'll end up with the expressions for the 1-parameter and the 2-parameter Margulies expressions that I introduced on Monday. So recall that from video 16.3, I can say that the excess chemical potential of species I equals RT ln of the mixture fugacity of species I divided by the mole fraction of species I in the liquid phase times the pure component fugacity. And recall that we defined this term inside the ln as the activity coefficient, such that we could simply say RT ln of the activity coefficient. Let me write those expressions down quickly. And also recall again that the mixture fugacity of species I is a function of temperature, pressure, and the composition, while the pure component fugacity of species I is a function of temperature and pressure, not the composition, because pure component fugacity assumes that the composition is 100% species I. So by rearranging this equation, we can obtain the following. We can say that ln of gamma I is equal to the excess chemical potential of species I divided by RT. Then recall that another term for the excess chemical potential, we can equally say that that is equal to the partial molar Gibbs free energy. So we can make that substitution. So we can say that the partial molar Gibbs free energy of species I, partial molar excess Gibbs free energy. We're starting to become very complicated in our terms here. Again, just remember that this is by definition, the chemical potential is equal to the partial molar Gibbs free energy. So if it's excess, then I just keep the excess. Furthermore, recall the definition of a partial molar property. So this is all the way back in chapter 11. We said in general, the partial molar property is equal to the partial derivative, so d of n theta molar by d n I at constant Tp and n, this is a capital N. Capital N and lowercase n I switch up all the time. This is the total number of moles. So constant number of moles of Nj, where J is not equal to I. So we had that definition from before. If I plug in this definition from before to apply it to the partial molar excess Gibbs free energy, recall that temperature and pressure are constant, so therefore I can just lump this all together. Therefore I can express this as ln of gamma I is equal to the partial derivative of number of moles, and then I'm just going to put this entire thing inside. So molar Gibbs free energy excess divided by RT with respect to constant number of moles of species I at constant Tp and Nj, where J is not equal to I. And made a minor mistake. There's no I there, so that should not have written an I. That's just the overall molar Gibbs free energy. Also remember from class 11, I had this summability relationship for any molar property theta. I can write that as xi partial molar theta I. Oh, for a binary mixture, let's say it's 1 and 2. All right, so x1 partial molar theta 1 plus x2 partial molar theta 2. This is from class 11. All right, so I can write that a different way. So I can say that if partial molar theta is equal to GE over RT, then I can write this following expression. I can say excess molar Gibbs free energy divided by RT for a binary mixture is x1 GE over RT plus x2 excess partial molar Gibbs free energy. This is becoming a mouthful. All right, so just by applying this equation, by saying that theta under bar is GE over RT, then I obtain this thing. And now I can say that because this ln of gamma is equal to partial molar excess Gibbs free energy, right? So we got here by saying that these two things were equal. I can substitute in these terms for an ln of gamma. So I can say that excess molar Gibbs free energy divided by RT is equal to x1 ln of gamma 1 plus x2 of gamma 2. All right, ln of gamma 2. I promise that we are almost to the point where we can start applying stuff. So this is the important relationship. Now, if I'm envisioning what a function of excess molar Gibbs free energy divided by RT would look like. So if I plotted that as a function of composition. So let's say I've got GE over RT as a function of X. And X is going to go from 0 to 1. I know what the excess molar Gibbs free energy must be for a molar composition of X is equal to 1. So at X is equal to 1, I have a pure component. At X equals 1, pure component A. Because I have a pure component, it must act as an ideal solution. Must act as an ideal solution because there literally are no other molecules to interact. Must behave, quote, ideally, in the sense of an ideal solution. Therefore, if it behaves ideally, then excess molar Gibbs free energy is equal to 0. And therefore, I have a data point at 0 there. Same thing for at X is equal to 0. I have pure component B. And the same thing must be true. I must behave ideally. So the excess molar Gibbs free energy must also be 0 there. So I've got 2 data points there. So how can I connect these 2 data points? The first possibility is I have a straight line. So let's see, dark blue is hard to read over black. So if I have a straight line that connects the 2, this is for the ideal case, right? Because excess Gibbs free energy is equal to 0 everywhere. GE over RT equals 0 everywhere. So there is no excess, there is no deviation from ideal conditions. What is the next simplest function that I can have? That is a symmetric parabola. So something like that. Keep in mind that I could have any function here. I'm just going in order of simplest to most complex. So green is simplest model that is not an ideal. That is not ideal. And this is a symmetric parabola. All right, so what is the expression for that function of the symmetric parabola? It is simply excess molar Gibbs free energy divided by RT is equal to A, x1, x2. All right, and if I express x2 as 1 minus x1, then I've got that parabola shape. Right, so this becomes a square. This is what gives rise to, this is literally what the 1 parameter Margulies expression is. 1 parameter Margulies. Then slightly more complex would be an asymmetric parabola, such as the one I'm showing here. In gold, so this is a parabola still that's been shifted. This is still second order in X, so I could get more and more complicated if I want, get cubic even, or higher order than that. But again, going in order of complexity. Gold is an asymmetric parabola. And the expression here gives rise to the 2 parameter Margulies, where I've got excess molar Gibbs free energy over RT is equal to x1, x2, A21, which is the first parameter, times x1 plus A12, x2, which is the second parameter. So this is the 2 parameter Margulies. 2-parameter Margulies. So how do we get from these expressions to an actual model for an activity coefficient? So on Monday, I told you how to calculate what the activity coefficients even are from these models. I'll discuss that next. All right, so let's talk about how to find what a mathematical model for gamma 1 and gamma 2 would be for the 1-parameter Margulies. So I've just simply copied what the definition for the 1-parameter Margulies model is there. So we've got a model for the excess molar Gibbs free energy divided by RT is equal to the parameter A times the mole fraction of component 1 times the mole fraction of component 2. And I've also applied our definition for the activity coefficient from above and applied it to a binary system. So where I had I's and J's before, I've just substituted them in for component 1 and component 2. All right, so now let's look at what happens here. So I'm going to plug in for this term, A, x1, x2. So let's do that in light blue. ln gamma 1 is equal to D n A x1, x2 over, with respect to dn1 at constant t, p, and n2. All right, so let's start simplifying things in this expression, keeping in mind that I shouldn't have changed the capital N. Anyway, by my notation, big N is equal to N1 plus N2. So remember, big N here is the total number of moles. In my notation, I always confuse little n and big N. There is no difference for me. Little n is equal to big N, just depends on what textbook you're using, which one they use. But the total number of moles is equal to the moles of component 1 plus the moles of component 2. And then x1, which is the mole fraction, is n1 divided by total n, or n1 over n1 plus n2. And similarly, x2 is equal to n2 divided by n1 plus n2. So let's plug all those in to obtain ln of gamma 1 is equal to D. And I've got big N now is n1 plus n2. I've got an A. I've got an x1, which is n1 over n1 plus n2. And times n2 over n1 plus n2. All with respect to changing n1 at constant tp and n2. And I'm just going to erase this so that it's clearer. I don't want to get too bogged down in being unclear. All right, can simplify things now. This n1 plus n2 will cancel with one of these n1 plus n2. Now the parameter A is a parameter, it's a constant, so that can come outside of the partial derivative. Similarly, n2 is being held constant in this partial derivative, so n2 can also come out of the partial derivative. So I could say A times n2 times the partial derivative now of n1 over n1 plus n2 with respect to changing n1 at Tp and N2. The next step is to apply the quotient rule. So I'm just going to copy the quotient rule. I'm going to pause and write the quotient rule. So need the quotient rule because here both the numerator and the denominator are functions of x. So let's go ahead and apply the quotient rule to take this partial derivative. And my a n2 is staying constant out front. Now I've got to take the derivative of the numerator, which is 1, and multiply it by the bottom function, which is n1 plus n2. I keep brackets, keep things organized, and I subtract the bottom function, which is, subtract the top function, which is n1, and multiply that by the derivative of the bottom function, and the coefficient of n1 here is 1. Okay, divide it all by the bottom function squared. So n1 plus n2 squared out. Next, I have an algebraic function which I can just multiply through. So I'm going to have a n2, and then one of these n1 plus n2 is going to cancel with another one, with one of the two on the bottom. So I'm just going to have n1 plus n2 on the bottom for the first term. and then minus a n2 n1 divided by, I'm going to write these separately, n1 plus n2 and n1 plus n2. And now what I've got is I've got an n2 over n1 plus n2, which is equal to x2. Same thing there. This is an x2, and here is an x1. So I'm going to factor back out the ax2 to obtain the final expression. So remember, this is all equal to ln of gamma 1. ln gamma 1 is ax2, and in parentheses 1 because it factors out minus x1. This is the expression for the activity coefficient of species 1. And also recall that you can express 1 minus x1 as x2. So this is also equal to ax2 squared. I'm not going to show you the full derivation, but you would do the exact same analogous process to obtain ln of gamma 2 is equal to ax1 squared. All right, so again, remember I showed you what this was a final result on Monday. This was just the derivation of that result. And you could do the same analysis. It would be slightly more complicated with a tougher partial derivative to take for the two-parameter Margulies expression. So again, I'll just remind you what your result that you get with the two-parameter Margulies expression is. So once again, you'd start the same exact way. I would just plug this entire expression for GE over RT into this partial derivative, and you can already see how it's going to become way more complicated. But do a similar analysis, and you'll end up with the activity coefficients for the two-parameter Margulies expression, which is ln of gamma 1 is equal to x2 squared times a12 plus 2 times a21 minus a12 times x1. Sure, there's plenty of simplification involved in here. I actually haven't worked this out for myself. This might be a good exercise to try this yourself and see if you can do it. a21 plus 2 times a12 minus a21 times x2. All right, so finally we've got our expressions for ln of gamma 1 and gamma 2 derived. And I've shown you where they've come from. And now finally in the next video, which is the final one for today, we'll be actually using these to fit some experimental data.